Hi, welcome to this lecture. We are going to talk about material characterization technique and in particular STM and AFM. STM stands for scanning tunneling microscopy and AFM stands for atomic force microscopy. Now, when we are going to see how the sensors are fabricated or how the transducer is fabricated, you have seen the lithography technique, you have seen PVD techniques, you have seen CVD techniques, right? And in that, when we deposit a film, right, then we need to understand the material properties of this film. Now, in case of ultrasound, it will be a piezoelectric material. What is piezoelectric? When you apply pressure, there is change in voltage. So, to understand the piezoelectric properties, right, we have to use something called X-ray diffraction. That will be taught as a separate class. We have to see the roughness of the film, which is using AFM, atomic force microscopy. We need to understand the tomography of the film, the topography of the film. We need to understand the electrical properties of the film, right, and all these material characterization properties are very important whenever you are going to fabricate any kind of sensor or transducers. So, today let us focus on STM and AFM. STM, as I told, it is a scanning tunneling microscopy. It was developed by Gerd Binning and Heinrich Rocher at IBM Zurich research laboratories in Switzerland, and you will be able to appreciate that everything that was discovered in the area of optics, in area of microscope, right, generated some kind of very valued research, and this particular work that was developed by these scientists resulted in a Nobel Prize in physics in 1986. The instrument works by scanning a very sharp metal wire. So, we will see here a very sharp metal tip which is here over a very close over a sample very close to the surface. So, it is just scanning, it is not touching, okay. It is having some distance between the metal wire and the sample, and by applying electrical current to the tip of the sample, we can image the surface at extremely small scale down to resolving individual atoms. The advantage of this particular microscopy is that we can see atoms by atoms surface tomography, okay. And there is a tunneling current amplifier, there is a distance control and scanning unit. So, you can understand where the probe is. There are piezoelectric tubes which will understand how much we are applying the how much the probe is down and what is the distance between the probe and the atoms. We can scan the tip, and the tunneling, when we say, so if you understand the quantum mechanics, then what quantum mechanics tells us? It tells us that electrons have both wave and particle like properties, but tunneling is an effect of the wave line nature. The top image, which is this one, what it shows? It shows that when an electron hits a barrier, the wave does not abruptly end, but taper off very quickly. You can see that it is tapering off, right, when it hits a barrier which is thick. This is a thick wall. Now, for a thick barrier, the wave does not pass the wall, which is obvious, and we can see that. However, the bottom image, which is this particular image, what we see that the scenario, if the barrier is quite thin, you see that if it is very thin, what will happen is the part of wave does get through, and therefore, some electrons may appear on the other side of the barrier. You can see this one, right, part of the wave may get through when the barrier is extremely thin. The number of electrons that will actually tunnel is dependent upon the thickness of the barrier. The actual current through the barrier drops off exponentially with the barrier thickness. To extend this description to STM, the barrier is the gap between the sample and the tip. Now, let us see where here. So, between the sample and the tip, there is a gap, okay. It is not touching the sample. This is the sample and this one is a tip, okay. This one is also a tip, just like we are scanning it, okay. So, now let us go back. So, what you see that there are two modes of operation. First is constant height and second one is constant current. So, in constant height, what we do is that the height remains constant and the variation of current will happen with lateral distance, and surface of density of the state and faster scanning rate is possible. If this is the sample, like this is the sample, what will we do is we will keep the distance between the sample and the tip constant, and if there is a valley or if there is a pit, right, or valley you can say that, and there is a mountain or a hill, right, there is a difference in the current that will flow through the system. So, that is one way of doing it. Second way of doing is that we will keep the current constant, and this tip will just scan across it, and depending on the change in the height of this tip, we can see what is the STM image that we get. So, in here the feedback adjusts the height to make the current constant, surface of the constant density of the state. In both the cases the computer software is used to add color and analyze the capture data. You can see here the image of a diffraction grating in 2D and 3D. We can also see that we can add different kind of colors to it. This is how the UI looks like, where you can understand the x, y, z moment, what is a change all the way to atom by atom. We can even see the blood cells, we can see materials like graphite, we can see and analyze different kind of materials. So, this is a YouTube video, so I will not play it because already on YouTube. So, just you can go here and look into that. Okay. So, so I do not want to play it, just you can copy this link and play it in your YouTube. You can write STM, it is very simple. Okay. So, now what are the advantages and disadvantages of the STM? The first one is that it has a high resolution images are possible, low power application and no damage to the sample because there is no physical contact between the sample and the tip. The disadvantages are following. First is we require vacuum because you need to control the height of this particular tip. Second is samples are limited to conductors and semiconductor because you are applying voltage at the sample and you are passing the current through it, right. So, either is constant current or constant height. Either we are looking at change in the current and the height is constant, or we are looking at the change in the height and current is constant. So, we need to have conductors and semiconductors. The cost is extremely high, the equipment very costly, surface preparation takes time, and the maintaining the tool sharpness is another issue. So, this is how the STM tool looks like. As you can see and you can appreciate, it is very complicated tool, right. It is not so easy to operate a STM, very costly also, but the advantages are immense. So, let us now move to another section, which is your atomic force microscopy. Atomic force microscopy is a tool that is used to understand the surface roughness of a film. So, again if you see, atomic force microscopy is a very high resolution type of scanning probe microscopy with a resolution of order of fractions of nanometer, more than 1000 times better than the optical microscopy. So, the information is gathered by feeling or touching because the probe will actually touch. So, suppose this is a sample and the probe is there. So, this probe will touch the tissue and you can scan it across the tissue, but it is actually making a physical contact. What will happen here is that you have to have a tip which can be a cantilever. You understand what is cantilever, right? So, I understand that this my hand is a part of cantilever and there is a tip of the cantilever. Now, if I move this thing, what will happen is, depending on the surface roughness of the film, cantilever will vibrate. So, if I shine a light on the cantilever and light reflects to the detector, right. So, there is a source. So, where should I bring it? Yeah, there is a source, there is a detector, light comes, hits the cantilever, goes to the detector, right. So, source and detector, source, light comes, hits the cantilever, goes to detector. Now, if I move this cantilever across the surface, it will vibrate, and that change in the light intensity the detector will get will from that we are able to generate the image. So, from that we can understand what is the roughness of the surface of the material. So, again it was developed by this great scientist, and they got Nobel Prize in 1986. The materials that we can investigate are thin films, thick film coatings, composites, glass, synthetic and biological membranes, metal, polymers, semiconductors, right. Almost every material we can understand the roughness by using atomic force microscopy. The another thing that we need to understand is we can understand the abrasion, corrosion, etching, lubricating, plating and polishing. With this all phenomenon we can understand. We can have the AFM can image material in nano resolution. You can see behind my back. So, can you just put me out of the scale? Yeah, thank you. So, now you can see I can also measure the force at nanoscale. alright. So, that is your important thing. There are several applications of this AFM, starting with life science application, where we can look at actin films, we can look at proteins, we can look at the erythrocytes, we can see bacteria, we can see DNA, we can understand the material surface science, for example organic film, transistor, ferroelectric materials, copolymers, polymers, we can look at the polymer film engraving, anodic oxidation, DNA on mica sheet, many examples of this AFM is there. As I told you, there is a laser which is a illumination, it is deflected off the cantilever. So, this is a one number which is the source or a laser light that falls onto this cantilever. This is a cantilever and this is a tip. 7 number is a tip of the cantilever, alright, or you can say probe tip. One, as you can see, laser, second is a mirror. So, here when the light reflects, it falls to the mirror and it goes to the detector. So, third one is a photo detector, fourth one is an amplifier, this one, fourth one is an amplifier, fifth one is a recorder and sixth one is a sample, this one is a sample. So, the probe tip actually touches here, okay. So, you have to bring this entire cantilever down and the probe tip will touch here, and then you can move the probe tip in either direction, either this direction or this direction, right, depending on how you are scanning the sample, alright. So, finally, the cantilever moves as scanned samples and reflects the laser beam. These are different kind of AFM tips. From the lithography, what we understood and how we learn is very simple, right. So, you start with the wafer, then it can be 111, it can be 100. I will prefer always 100 orientation to create a diaphragm. Diaphragm you can create using micro machining, right. We have learned this thing. So, now if you have oxidized silicon wafer, you can grow oxide. This is your silicon dioxide, and you pattern silicon dioxide such that you can form a window. You etch this window, that means you are etching silicon. Silicon can be etched using wet etching or dry etching, right, wet etching or dry etching. After that, what you do is you can further pattern the silicon dioxide such that it is only here and here, and then you again etch silicon using wet etching or dry etching. Let us say we are using wet etching. Then what we do is, after this you can remove the silicon dioxide and further sharpen it like this by etching it. Then you again grow silicon dioxide everywhere, as you can see everywhere silicon dioxide is there. Then what you do is you open the etch the silicon dioxide from here and completely etch the silicon which was here, right, this part. Now you can see it is gone. After this, what you do is you can do front to back alignment, and then you can etch from back side. This will be a wet oxidation, because of wet etching, because you have a angle which you have created here. If it is dry etching, then you will have a sharp cantilever like this. Let me just draw it for you, right, like this. So, the angle that you create here versus the angle that you create here, that you can very easily see what kind of etching technique can be used. Finally, you can dip this cantilever in BHF so that the oxide will be etched and you can have your cantilever. These are normal tips, there are super tips, there are ultra lever, there are diamond coated tips, FIB sharpened tip, gold coated tips. Depending on the application, you can have different kind of cantilever tips. This is another process where you can have multiple tips simultaneously. This is a SOI wafer. SOI stands for silicon on insulator. This is a silicon, this is silicon dioxide, this is silicon, this is silicon dioxide. Okay. Now, the top layer is also SiO2. This silicon is sitting on an insulator, that is why we call this wafer as a SOI, silicon on insulator. Then you oxidize silicon on insulating wafer, that means SiO2 is on the front, SiO2 is in the back, and then you perform lithography so that the silicon dioxide from the back is etched, as you can see from this particular image. After that, what you do is you do the etching so that you can create a window. You can see here on the front side you have created a window, and then you have etched the silicon. After that, you can pattern the silicon dioxide as shown here. After that, you sharpen this by etching the silicon completely, and there is a etch stop here, because in silicon etchant silicon dioxide will not get etched. The ideal situation is that silicon dioxide should not get etched at all. But practically silicon dioxide will get etched, but the etching rate of silicon dioxide is way lower compared to silicon. That is why we say silicon dioxide will work as a etch stop. when we are etching silicon. After that you can have you can create the tips, as you can see here, by using the etching technique. Then you can grow silicon dioxide again, create a window, and then remove silicon dioxide from here, and then you can etch the wafer completely like this. So you can have two cantilevers, cantilever number 1 and cantilever number 2. So multiple cantilevers you can fabricate using the microfabrication technique. Let me go to the so this is again a YouTube video. So I am not going to play it, just to make sure that we you can always go to YouTube and see how this AFM would work. So I am not going to play it. Please go back to this YouTube link and look at the video. Okay. So now we are going to further little bit again recall about AFM. So atomic microscopy is a technique by which we can measure the roughness of a film. We have a cantilever for probing the sample. We have a laser diode, we have a mirror, we have photosensitive detector, there is amplifier, there is error which we can measure, so that what is actual signal minus set point, and then you have a piezoelectric scanner, and you have computer for recording. Same thing is shown in both the images. This is a little bit a detailed image number 1. This is easiest way to say the same thing, right. Now the principle of operation of AFM is, AFM consists of cantilever with a sharp tip and its end that is used to scan the specific specimen. Cantilever is typically silicon or silicon nitride. When the tip is brought into proximity to a sample surface, the laser beam activates and the force between the tip and the sample leading to a deflection of the cantilever. Finally, depending on situation, and the forces that are measured in AFM includes mechanical constant force, van der Waals force, capillary force, chemical bonding and electrostatic forces. AFM scanners are made up from piezoelectric material. Why? Because you need it will keep on vibrating, and then we can corresponding understand the change in the voltage. Also piezoelectric materials can be barium titanate, can be zinc-rhodium titanate. Whether they elongate or contract depends on upon the applied voltage. Traditionally, the tip or sample is mounted on a tripod of piezoelectric crystals, with each responsible for X, Y and Z scanning. So it does not scan in theta but X, Y and Z. And because of differences in material or size, the sensitivity varies from scanner to scanner. So AFM can be used to measure, to image, to analyze. You can see a image from AFM, and here you can see the change in the Z delta, which is the change in the variation of the film with respect to distance. You can have 2D images, you can have 3D images using AFM. The tip is brought within a nanometer of the sample, then it is a van der Waals force will act. Radius of the tip limits the accuracy of the analysis. Sharper the radius, the better the accuracy. Stiffer cantilevers protect against sample damage because they reflect less in response to small force. So what we can do? We can do the morphology characterization, we can understand surface roughness, we can understand the physical properties, swelling, cohesiveness, smoothness. There are different kind of method to measure the roughness of the film. The first one is contact mode, where the cantilever will make a hard contact and it stable samples in air or liquid. Non-contact mode, which is non-invasive sampling, where the contact is not there. And third one is a tapping mode, where no shear and damaging samples no shear will be there, but there can be possible damage to samples. Anyways, the point is, for the contact mode, the measures the repulsion between tip and sample, because it makes a physical contact with respect to the sample. The forces of the tip remains constant. The problem here is that excessive taking of force applied by the probe to the sample, and that will actually affect the sample. Since you are scanning it by applying a force to a sample, the material that is there on the sample will get damaged. The second mode is a non-contact mode, where the measures the attractive forces between tip and sample. Tip does not touch the sample, the van der Waals force will act, and the problems here is that it cannot be used in fluid. Used to analyze semiconductors, does not degrade or interfere with the sample. So it can be used better for soft samples, biological samples. The third one is a tapping mode, where the tip vertically oscillates and the frequency is about 50,000 to 5 lakh cycles per second. Oscillation amplitude reduced as probe contact surface due to loss of energy. Advantages are it can overcome the problems associated with friction, addition, electrostatic force, because we are not scanning it, we are tapping it, and is more effective for larger scanning size, because you can do this tapping in a faster way compared to the contact mode. The contact mode and dynamic mode, which is non-contact mode, is shown in this particular image, where you can see that how both can be used with respect to surface tension, with respect to tapping. When the fluid layer is there, what can be how the amplitude will change compared to when compared to how when there is a contact mode. The tapping mode has its advantages, but in general, if you want to understand the advantages and limitations of AFM, the following are the advantages. The sample preparation is very easy compared to STM. It works in vacuum, air and liquids, accurate height information. We can do live sample analysis, we can use 3D imaging, we have dynamic environment, surface roughness quantification is possible. The limitations are limited vertical range, limited magnification range, data not independent of tip or sample can be damaged, and limited scanning speed. The AFM is a versatile tool in general that can be used to understand the topography, properties of surfaces, properties of single molecules, forces within molecules, but you always have to understand that when it comes to experimental conditions and artifacts, there will be a lot of artifacts that we need to take care of. The future of AFM, which is now actually, because this slide is little bit older, but the future lies in fabrication, and sharper the tips we can fabricate using microfabrication process. Second, development of more flexible cantilever spring and less damaging and non-sticky probes is something that if we start using it, we can further enhance the image quality of the cantilever. This is an example of a piezoresistive micro cantilever. So let us quickly understand this particular example. We have a probe tip, okay, and then you have a piezoelectric material that you are diffusing into a silicon. These are contact pads, contact pad 1, contact pad 2, CP1, CP2. These are gold, okay. So somewhere that you see this contact pads, this one and this one are here, okay, and the big one, it goes all the way out. So here what you see in this SEM image, these two are this one and 2, okay. You can see there is a SU8 tip, and you will appreciate the fabrication technique because we have used a deep reactive ion etching, and you can see a completely released cantilever. So you start with a SOI wafer, which is silicon on insulator. There are certain colors here. Silicon nitride is purple, silicon dioxide is green, silicon is grey, gold is of course gold color, boron resistor is yellow, cross linked SU8 material is blue, boron contact is orange in color. So orange or light pink, whatever you want to say. So we start with the silicon dioxide wafer, we grow silicon dioxide on SOI, and then you create a window, then you diffuse boron, right, which is P type material onto this into the silicon. After that you again create a silicon dioxide, then you create a window, diffuse high P++ boron as a contact pad. Here this 2 and 1 is P++, this one where the cantilever is there, I am sorry, it is cantilever somewhere here, this is P type, okay. Now the question is why we have contacts of this cantilever 1 and 2 P++, and why cantilever is P, piezoresistive material, right, resistor is P, is to make sure that the contact further we take it, which is here, this whole contact pad, right, is gold, everything is gold. So to have a ohmic contact, we need to make sure that the conductivity of the contact pad is high, that is why we have P++. After that you can make a gold contact to take the contact pads outside, and then you have silicon nitride deposition using PECVD because it is a technique at which we can use a technique which is used at lower temperature for growing silicon nitride and silicon dioxide. After that you can create a window, as you can see here, here and here, right. Then you can etch silicon, after etching silicon dioxide. So when you create a window you see silicon dioxide. This silicon dioxide you can etch using BHF. When you etch silicon dioxide using BHF, you again encounter another silicon dioxide, and then what you do, you can coat SU8, spin coat SU8, pattern SU8. After spin coating SU8 and patterning it, on the back side you do front to back alignment and pattern the back side such that first you remove silicon nitride followed by silicon dioxide. There are silicon dioxide and silicon nitride, and then whatever the silicon you can see, you can go for DRI so that you can get the final cantilever, which is shown in this particular image, right. This is a final SEM image of piezoresistive micro cantilever. Okay, we will repeat it once again. First step is SOI, second step is grow silicon dioxide, third step is to create a window for piezoresistor, fourth step is to dope boron resistor, fifth step is to grow silicon dioxide, sixth step is to create window for P++ contact pad for the piezoresistive microcantilever. Next step is to sixth, right. So, yeah, here we have opened the contact, and then next step is to actually dope P++, followed by 8th step. Step number 8 is where we have gold contact pad. The 9th step is where we do the silicon nitride growth, and then followed by patterning. 10th step we have removed or etched silicon dioxide and etched silicon. 11th step what we do is we grow we spin coat SU8 and pattern it to form cantilever tip. In the next step what we do is we etch the we do the front to back alignment and then etch silicon nitride from the back side, from this side, and also silicon dioxide so that we can see silicon. And in the final step what we do is we can go for DRI so to etch the silicon. So, this is how the piezoresistive microcantilever can be fabricated. So, I hope that now you understand the importance of AFM, importance of STM. We can also fabricate piezoresistive microcantilever. This resistive, now we are saying resistive, that means you apply pressure, there is change in resistance. So, this can also be used for measure the roughness of the film. For example, if there is a piezoresistive cantilever and if this is a cantilever, right, this my hand with a tip, and you are applying or scanning it across the sample, what happens, depending on the roughness this will bend. When this bends, the piezoresistor that is embedded or diffused into it, right, the resistance would change because of the pressure, because of the bending, the stress that is created in the piezoresistor. So, that will show the change in resistance depending on the stiffness of the material that we have deposited. It can be used for understanding cell analysis, it can be used for understanding tissue elasticity, and so on and so forth. So, the beauty of AFM is not only it can be used for cantilevers which works on laser diode and detector, but we can also modify this technique and use piezoresistor so that the change in the output instead of is a light deflection is a resistance that changes when you apply a pressure. Piezoresistor, apply a pressure, change in resistance. Piezoelectric, apply pressure, change in voltage. So, with that I will stop lecture here and I will see you in next class. Till then you take care. Bye for now.